In this video, we'll work out two examples of solving initial value problems. So we have two problems here, and we're going to work through both of them. So for the first one, we have y double prime plus 2y prime minus 15y equals 0, with integrations at 0 being 1 and minus 2 respectively. Now, we can look to solve this. So the first example, we first get our characteristic equation. So that's going to be r squared plus 2r minus 15 equals 0. And this actually factors as r plus 5, r minus 3. You could also go at this via quadratic formula if you didn't see right away that it factored, and that would give you something like r equals negative 2 plus or minus the square root of b squared is 4 minus 4ac is plus 60 over 2, and if you work that, you will get minus 5 and plus 3, because those are our two roots here. Which means we are not even in the complex valued case at all. This is a real valued one that has real roots, and so we're back in the earlier case, which is exponentials. This means our general solution is going to be c1 e to the 3t plus c2 e to the minus 5t. And I want to try to meet our initial conditions. So the derivative here is going to be 3c1 e to the 3t minus 5c2 e to the minus 5t. And I can plug in 0 to both of those to get that 1 should equal c1 plus c2, because exponentials all go away. And minus 2 should equal 3c1 minus 5c2. Then to solve this, I'm going to multiply this first equation by 5, and then add them together to cancel out the c2 terms. So I do that, I will get 5 minus 2 is 3 on the left. I will get 5 plus 3c1 is 8c1 plus 0c2 as expected. That gives me that c1 is 3/8. And plugging into the first equation, c2 then must be 5/8. We can then check real quick. 3c1 is going to be 9/8. And then minus 5 is going to be minus 25 over 8, which will give me 16 over 8, which is minus 2 as expected. So my solution here is 3/8 e to the 3t plus 5/8 e to the minus 5t. Now for the second, we should hopefully see some complex numbers. That was sort of the point of this set of videos. The second one we had, this equation here, y double prime plus 2y prime plus 5y equals 0, with y of 0 equaling 2y prime is equals 1. Again, we go to solve this. We get characteristic equation of r squared plus 2r plus 5 equals 0. This does not factor. Let's try quadratic formula. R is negative 2 plus or minus the square root of b squared is 4 minus 4ac is minus 20 over 2. It definitely wasn't going to factor because this part here is imaginary. So we're going to end up with complex numbers. So I end up with a negative 2 plus or minus root negative 16 over 2. Or a negative 2 plus or minus 4i over 2. Or a negative 1 plus or minus 2i. Which means the roots are negative 1 plus 2i and negative 1 minus 2i. So that means, based on our method for complex numbers, this means that our general solution is going to be y of t is c1 e to the at. A here is negative 1, so minus t. Cosine of bt, b here is 2, so cosine of 2t. And then plus c2 e to the minus t again, and now sine of 2t. These patterns are always the same. The exponent's always the same, and the part inside the sine or cosine is always the same number, and they match the real and imaginary parts of the root respectively. We can then differentiate this, and this here is two products. It's going to be longer, but it still works out the same way. So here y prime is going to be a negative c1 e to the minus t cosine of 2t when I differentiate the e to the minus t term. And then minus a 2c1 e to the minus t sine of 2t when I differentiate the cosine term. And now for c2, minus a c2 e to the minus t sine of 2t. And then plus 2c2 e to the minus t cosine of 2t. And now our initial conditions were 2 and 1 respectively. So we have 2 and 1 equaling these functions plugging in 0. Now the benefit here is I have a sine function here. When I plug 0 into sine, it goes away, and cosine goes to 1. So when I plug 0 in here, this entire term vanishes because sine of 0 is 0. So I'm left with just c1. For the derivative, this sine term is gone, and this sine term is gone. So I'm left with just a minus c1 plus 2c2. Because e to the minus c also goes to 1 when t goes to 0. This tells you that c1 must be 2, and then 1 equals negative 2 plus 2c2, meaning that 2c2 equals 3, or c2 is 2/3. Therefore, my solution is y of t is 2 e to the minus t cosine of 2t plus 2/3 e to the minus t sine of 2t. And as a recommendation, you should probably get in the habit of always putting the cosine and sine terms in the same order when you do these, like for what c1 and what c2. That'll make it easier to keep it straight in your head when you try to actually solve these problems. So there's two examples. There's an example of solving the real method that we've done before, and how it looks similar in process and setup to the complex method. The only difference is what your solution actually looks like. For the real case, you're just getting exponentials and nothing else, but for the complex case, you have exponentials with trig functions attached to them. It makes this derivative more complicated, but the process is the same: differentiate, plug in 0, and match all of these things up to what they need to be. So that's the idea of how those work and how you go about solving these equations. For second order equations, both with real roots and with complex roots.